Alkenes are unsaturated hydrocarbons. The characteristic reaction of alkenes is addition to the carbon-carbon double bond. In chemistry, a carbon-carbon double bond is denoted by a double dash. The general form of addition to an alkene may be represented as where A, B can be various compounds. Through addition reactions, alkenes can be converted into many compounds with different functional groups for synthetic purposes. A typical addition reaction is the hydrogenation of alkenes to give alkanes, where platinum, palladium, or nickel is used as the catalyst. In hydrogenation, H2 is added to a multiple bond, such as a double bond. An example here is the addition of hydrogen to the double bond of ethene to form ethane, in which one HH bond of the hydrogen molecule and the pi component of the ethene's double bond are broken. Two CH bonds of an alkane are formed. The overall reaction is exothermic. The uncatalyzed addition of hydrogen to alkene is very slow. In the presence of a catalyst such as platinum, palladium, or nickel, the rate of hydrogenation increases dramatically, even at room temperature. The most commonly used catalyst in the hydrogenation of alkene is platinum. Look here, an ethene molecule is very close to the surface of the metal catalyst. Some hydrogen molecules are also approaching the catalyst. When the hydrogen molecules settle on the surface of the catalyst and react with the metal atoms, a relatively strong hydrogen-hydrogen bond is broken and is replaced by two weak metal hydrogen bonds. Meanwhile, the ethene molecule also lands on and reacts with the metal catalyst. Its carbon-carbon double bond interacts with the metal atoms. Two weak carbon-metal bonds are formed. A hydrogen atom is transferred from the catalyst surface to one of the carbon atoms of the carbon-carbon double bond. A new carbon-hydrogen bond is formed. The second hydrogen atom is transferred to the intermediate. An ethane molecule is formed. Finally, the newly formed ethane molecule departs from the metal surface, leaving the site to other hydrogen atoms and ethene molecules, and the process repeats. What are the end products when an asymmetrical alkene reacts with hydrogen halide? An asymmetrical alkene is an alkene in which the two carbons of the double bond bear different atoms or side groups. Bu1ene and 2-methylpropene are two of the examples. In 2-methylpropene, there are two methyl groups on one carbon atom of the double bond and two hydrogen atoms on the other carbon atom. In Bu1ene, there are one ethyl group and one hydrogen atom on one carbon atom of the double bond, and two hydrogen atoms on the other carbon atom, respectively. By probability, a hydrogen halide can be added to an asymmetrical alkene in two ways. However, in practice, such an addition is highly regioselective, favoring one product over another. How does it come? In 1870, Russian chemist Vladimir Markovnikov asserted the specific pattern of hydrogen halide addition to alkenes. When an asymmetrical alkene reacts with a hydrogen halide, the hydrogen is added to the carbon with more hydrogen substituents, and the halogen to the carbon having fewer hydrogen substituents. This is the Markovnikov's rule. So, when 2-methylpropene reacts with hydrogen bromide, it gives 2-bromo-2-methylpropane and 1-bromo-2-methylpropane. Which one is the major product? By Markovnikov's rule, the major product is the one in which the hydrogen atom is added to the carbon atom with more hydrogen atoms. Here, in the carbon-carbon double bond, the carbon in green carries 2 hydrogen atoms, while the carbon in orange has none. H goes to the green carbon, and Br to the orange carbon. 2-bromo-2-methylpropane is the major product. The reaction mechanism is depicted below. Firstly, 2-methylpropene accepts a hydrogen ion from hydrogen bromide to give a species that bears a positive charge on a carbon atom. We call it carbocation. The newly added hydrogen ion is attached to the carbon of the double bond having more hydrogen, that is, the carbon in green. Then, a halide anion is added to the carbocation to give the major product, 2-bromo-2-methylpropane. An alkene reacts rapidly with chlorine gas or bromine in an organic solvent to give dihaloalkane. The reaction mechanism between ethene and bromine involves 2 stages. Firstly, one of the bromine atom is attached to both carbon atoms, carrying a positive charge. In this stage, a positively charged bromonium and a negatively charged bromide ion are formed. Then, the bromonium ion is attacked by the other bromide ion from the back to give dibromoalkane. Haloalkanes can be classified into primary, secondary, and tertiary haloalkanes. Here are some examples. In primary haloalkanes, the carbon carrying the halogen atom is only attached to one alkyl group. In secondary haloalkanes, the carbon holding the halogen is attached directly to 2 alkyl groups, which may be the same or different. In tertiary haloalkanes, the carbon atom holding the halogen is attached directly to 3 alkyl groups, which may be any combination of same or different. Substitution reactions are typical reactions of haloalkanes. Here illustrates the use of an anion, Y- of a metal salt to substitute for a halogen, X, of a haloalkane. In this example, the bromine atom in the haloalkane is simply displaced by a hydroxyl group, hence a substitution reaction. Propanol is formed after the displacement of the bromine atom. The reaction mechanism for reactions between primary or secondary haloalkanes and sodium hydroxide can be represented by a single elementary step. What is a single elementary step? In a single elementary step, the major products are formed after only one key step. Revisit the substitution in which 1-bromopropane reacts with sodium hydroxide to form an alcohol, propanol, and sodium bromide. Convert the equation into an ionic equation. In effect, it is the hydroxide ion that attacks the carbon atom holding the bromine, and the bromine departs as a bromide ion. In this reaction, the hydroxide ion reacts with the 1-bromopropane to form the unstable transition state. The major products are formed after only one key step. This one key step is also the rate-determining step of the reaction. The formation of a covalent bond between the carbon and the hydroxide ion at the unstable transition state facilitates the cleavage of the bond between the carbon atom and the bromine. It is just like the hydroxide ion pushes the bromine off from the carbon atom. Note that the hydroxide ion attacks the carbon atom from the side opposite to the leaving group, in this case, the bromine atom. We call it a backside attack. At the transition state, the carbon atom is partially bonded to both the incoming hydroxide ion and the departing leaving group bromide ion. At the same time, the hydroxide ion begins to share a pair of its electrons with the carbon atom. The bromine atom takes the pair of electrons from the carbon-bromine bond and leaves as a bromide ion. The rates of the single elementary steps when bromomethane, bromoethane, 2-bromopropane and 2-bromo-2-methylpropane reacts with the hydroxide ion differ greatly. The least reactive member among them is 2-bromo-2-methylpropane. But why? Remember that the attacking agent, hydroxide ion, approaches the haloalkane from the side opposite to the leaving group. In bromomethane, the 3 hydrogen substituents are just small obstacles to the approaching hydroxide ion, so the substitution reaction occurs very quickly. Replacing the hydrogen substituents in bromomethane with the methyl groups one by one somewhat shields the carbon from the attack by the hydroxide ion. Therefore, for the case of tertiary haloalkane, the backside approach to the tertiary carbon of 2-bromo-2-methylpropane is almost blocked, making the reaction through the backside almost shut down. We call this spatial obstacle steric hindrance. Overcoming this hindrance requires much initial energy. That's the reason why tertiary haloalkanes are practically inert to this type of substitution. Then, how do tertiary haloalkanes undergo substitution? They take another reaction route to achieve it. Let's have a look at the hydrolysis of the tertiary haloalkane, 2-bromo-2-methylpropane. This is the overall reaction. Here, the bromine atom is substituted by a hydroxyl group. The overall reaction can be divided into 3 elementary steps. Firstly, the haloalkane dissociates to give a halide ion and a species that bears a positively charged carbon atom, that is, a carbocation. This is the slowest step. We call it the rate-determining step. Secondly, the carbocation formed in step 1 reacts rapidly with a water molecule to give an alkyloxonium ion which is positively charged. The third step is a fast acid-base reaction. Water acts as a base to remove a proton from the alkyloxonium ion to give the end product, 2-methylpropane-2-ol. To conclude, unlike primary and secondary haloalkanes, tertiary haloalkanes mainly adopt this reaction route to undergo substitution reaction.